Hi, Ann. Today, in this morning, I'm going to discuss about the rotary pumps. Rotary pumps are generally positive displacement pumps, which displace a known quantity of liquid with each revolution of the pumping elements, and for the functioning of these pumps, no priming is required when they are started. Rotary pumps always deliver a constant, smooth flow regardless of pressure variations. These are versatile, and their popularity is due to their relevant and relative compact design and high viscosity performance. In rotary pumps, the pumping element designs includes gears, lobes, rotary pistons, vanes, and screws. And these pumps are named after these designs or pumping elements. Now, in this slide, we are going to see the construction and working of rotary pumps. That means main parts of the rotary pump. Here, this is the suction area, and this is the rotor, and surrounding is the casing, and we finally have a handle or a motor attached to rotate the rotor inside, and finally, this is the outlet where the discharge takes place. Rotary positive displacement pumps have very tight internal clearances, which minimize the amount of liquid that slips back from the discharge to the suction side of the pump. Rotary pumps are designed so that the rotary pumping elements draw the fluid at the suction port into the pumping cavity, transport it through the pumping elements, and force it through the discharge port into the system. The geometry of the pump elements and pumping cavity determine the volume of the fluid pump per revolution of the shaft. This volume is called the displacement. Most rotary pump types are configured for fixed displacement. However, they can produce variable flow rates by varying the shaft speed. Following are the uses of the rotary pumps. Rotary pumps can pump not only thick and viscous liquids such as oils or burners, soaps, and cosmetics, sugar, syrups, and molasses, dye, inks, bleaches, vegetables and mineral oils, greases, etc. But they can also pump lighter liquids such as gasoline, alcohol, etc. The advantages of rotary pump includes less maintenance, less weight, compact size, not requiring priming when they are started, delivering high pressure liquids, relatively smooth outputs, especially at high speeds, and pumping viscous liquids. Other advantages of rotary pumps. But these pumps have certain limitations also, which are more expensive. They cannot be used for fluids containing suspended solids and should not be used with the discharge closed. Types of rotary pumps include single rotor and multiple rotor. When there is only one rotating pumping element in the pump, then it is called single rotor pump, which includes rotary vane pump, rotary screw pump, and rotary piston pump. When the pumping elements are multiple, then such pumps are called multiple rotor pumps, which also includes rotary gear pumps, rotary lobe pumps, and rotary screw pumps. So this is the schematic view of a multiple rotor gear pump. A gear pump uses the machine of gears to pump the fluid by displacement. There are two main variations in the gear pumps. One is external gear pumps, which use two external spur gears, and internal gear pumps, which use an external and an internal spur gear. Here is the view of the external gear pump, in which there are two spur gears which mesh with each other. The liquid comes here in the suction port, and when the gears rotate, the liquid is pulled into the gears. When they are meshed, the liquid gets pressurized and discharged into the discharge port of the pump. This slide explains the working of the gear pump. These pumps come with the straight spur, helical, or herringbone gears. Straight spur gears are easiest to cut and they are most widely used. Helical and herringbone gears run more quietly, but they cost more. Usually, small external gear pumps operate at 1750 to 3450 RPM, whereas larger gear pumps operate at 6400 RPM. External gear pump. The design of the external gear pump allows them to be made to closer tolerances than internal gear pumps. External gear pumps handle viscous and water-tight liquids, but speed must be properly set for thick liquids. The pumps do not perform well under critical suction conditions. Volatile liquids tend to evaporate locally as the gear spaces expand rapidly. The simple gear pump consists of two spur gears meshing together and revolving in opposite directions with a casing to produce flow. One is the driving gear and the other is the driven gear. Each gear in the external gear pump is supported by a shaft with the bearings on both sides of the gear. Because the gears are supported on both sides, external gear pumps are used for high pressure applications such as hydraulics. Clearances between the gear teeth outside diameter of the gear and casing and between the end face and the casing are only a few thousandths of an inch. As the gears turn, the gears unmesh and the liquid flows into the pockets that are vacated by the meshing gear teeth. This creates the suction and that draws the liquid into the pump. The liquid is then carried along in the pockets formed by the gear teeth and the casing. On the discharge side, the liquid is displaced by the meshing gears and forced out through a discharge side of the pump. This is the schematic view of the internal gear pump, which consists of an internal spur gear and an external spur gear. Here also, the liquid is drawn into the through the suction port when the gears unmesh, carried along the pockets, and they get the liquid gets compressed at the and then discharged at the delivery port of the pump. The violet one is the driven gear, and the yellow one is the driver gear. The speed of the internal gear pumps is considered relatively slow compared to the centrifugal pumps. Only 1500, 1150 RPM can be achieved. Because of the ability to operate at low speeds, internal gear pumps are well suited for high viscosity applications as the suction conditions call for a pump with minimal inlet pressure requirements. For each evolution of an internal gear pump, the gears have a fairly long time to come out of the mesh, allowing the spaces between the gear teeth to get completely filled. These pumps can handle small suspended particulate in abrasive applications, but gradually wear and lose performance. The liquid enters into the suction port between the rotor and the idler gear teeth. The liquid travels through the pump between the teeth of the gear within a gear principle. The crescent shape, which we have seen in the image above, divides the liquid and acts as a seal between the suction and discharge ports, which do not allow the reverse flow of the liquid from the discharge to the suction side. The pump head is now nearly flooded just prior to forcing the liquid out of the discharge port. The intermeshing of the idler and the rotor form the locked packets for the liquid, which assures volume control. The rotor and the ideal gears meshed completely to form a seal equidistant from the discharge and suction ports. This seal forces the liquid out of the discharge port. The advantages of gear pumps are as follows. High pressures and low capacities handle a wide range of viscosities, relatively simple to maintain and rebuild, quiet operation. The disadvantages are tight tolerances, requirement of tight tolerances. Applications of gear pump include petrochemical industries, chemical industries, paint and ink, pulp and paper, and food industry also. Okay. This is about the rotary pump. Thank you.